What is energy? Stop for a second and actually try to answer that question. Not with a metaphor, not with an example. What is energy? You might say it's the stuff that makes things move, the fuel that powers your car, the electricity in your wall socket, the calories in your food. But here's the problem. None of those answers are actually correct. And Richard Feynman, one of the greatest physicists who ever lived, knew this would happen. He knew that almost everyone, including most physics students, fundamentally misunderstands what energy actually is. You see, we're about to expose something unsettling, something that will make you question whether you've ever truly understood anything about the physical world. Because energy is not a thing. It's not a substance. It's not a fluid flowing through wires or a glowing cloud surrounding objects. It is something far stranger and far more beautiful. Feynman described it like this. Imagine that nature has a hidden accountant. This accountant keeps track of a single number, just one abstract mathematical quantity. And no matter what happens in the universe, no matter how chaotic things get, this number never changes. Particles collide, stars explode, you eat breakfast. And through all of it, this mysterious number remains constant. That number is what we call energy. But if you're thinking, okay, so it's a number, but surely that number represents something real, something physical, then you're still trapped. You're still thinking like everyone else. And to prove it, let's look at something so simple, so mundane, that you've experienced it thousands of times without ever questioning what's actually happening. Let's look at a light bulb. You walk into a dark room. You flip a switch. Instantly, a light. The bulb turns on. Energy has clearly traveled from the power plant through the wires in your walls and into that bulb. Right? That's the story we tell ourselves. That's what feels obvious. Electrons flowing through copper wire, carrying energy like tiny delivery trucks, bringing power to your light bulb. But here's where things start to fall apart. Those electrons, the ones you think are delivering the energy, they move unbelievably slowly. We're talking about drift velocity here, the actual speed at which electrons move through a conductor. And it's not fast. It's not even close to fast. Electrons in a typical wire move at roughly 1 millimeter per second. That's slower than a snail, literally slower than a garden snail crossing your sidewalk. Think about what that means. Your light switch might be 5 meters from your bulb. If energy traveled with the electrons, if it depended on those sluggish particles crawling through the copper, your light would take over an hour to turn on. You'd flip the switch, go make dinner, watch a show, come back, and maybe, just maybe, the light would finally flicker to life. But that doesn't happen. The light turns on instantly, or rather, it turns on at the speed of light, roughly 300 million meters per second. So where is the energy? If it's not riding along with the electrons, if those electrons are barely moving at all, then where the hell is the energy that lights your bulb? This is the trap. This is where your intuition completely betrays you. The answer is so counterintuitive, so bizarre, that when physicists first figured it out, many refused to believe it. The energy is not inside the wire. It's not flowing through the copper. It's not being carried by electrons. The energy is outside the wire. It's in the space surrounding the conductor. It's in the invisible electromagnetic field that exists in the air, in the vacuum, in the seemingly empty space around the wire itself. And this isn't speculation. This is mathematics. This is the Poynting Vector, a precise calculation discovered by John Henry Poynting in 1884, and it tells us exactly where energy flows in an electromagnetic system. Picture this. Imagine the wire is a monorail track. You've always thought the train, the energy, runs along the track, supported by the metal rails. But the truth is stranger. The track is just a guide. The train, the actual energy, is levitating around the track, flowing through the space surrounding it. The wire doesn't carry energy. The wire creates the conditions. The electromagnetic field that allows energy to flow through space nearby. Let that sink in for a moment. Energy is not a property of matter. It is a property of fields, of space itself. Now, if you're feeling uncomfortable right now, good, you should be. because we're about to go deeper. We're about to dismantle another piece of your intuition, and this one involves magnets. You've played with magnets. Everyone has. You know they attract and repel. You know there's a magnetic field, invisible but real, that reaches out through space and pushes or pulls on other magnets. But have you ever asked yourself, what is that field made of? Where does that force actually come from? Here's the answer that will break your brain. Magnetism doesn't exist. Wait, what? Magnetism doesn't exist, but I can feel it. I can see it work. How can you say it doesn't exist? Because magnetism is just electricity viewed from a different reference frame. It's a consequence of special relativity. It's what happens when electric fields are observed by someone who's moving relative to the charges creating those fields. Let me explain. Imagine a wire carrying an electric current. That current is nothing more than electrons moving through the conductor. Now, if you're stationary, standing next to that wire, you observe a magnetic field around it. But here's the magic. If you were moving along with the electrons, matching their velocity exactly, the magnetic field would disappear. It would vanish completely. Instead, you'd observe a pure electric field. So, which is real? The magnetic field or the electric field? The answer is both, and neither. What's real is the electromagnetic field, a single unified entity that appears different depending on your motion, depending on your frame of reference. Magnetism is not a separate force. It is the relativistic correction to electricity. But why does motion change what we observe? This is where Einstein comes in. This is where we have to confront one of the strangest facts about reality. Space and time are not fixed. They bend. They stretch. They contract depending on how fast you're moving. Here's the picture. Imagine a wire with stationary positive charges and moving negative charges, the electrons. If you're at rest relative to the wire, the positive and negative charges appear evenly distributed. The wire is electrically neutral, no net electric field. But there is a magnetic field because the electrons are moving. Now, imagine you start moving alongside the electrons. Suddenly, due to length contraction, a prediction of special relativity, the spacing between the moving electrons appears to change relative to the stationary positive charges. The wire is no longer neutral from your perspective. You now observe an electric field. The magnetic field has transformed into an electric field simply because you changed your velocity. This is not a trick. This is not an illusion. This is the geometry of space-time revealing itself. Magnetism is what electricity looks like when you account for the fact that space contracts along the direction of motion. Energy and momentum and charge and fields. They're all part of a single interconnected structure, a structure that changes appearance depending on how you move through it. And if that wasn't enough, let's go further. Let's connect this back to the most famous equation in all of physics. E equals mc squared. You know this equation. Everyone knows this equation. Energy equals mass times the speed of light squared. But what does it actually mean? Most people think it means mass can be converted into energy, like in a nuclear bomb, and that's true. But it also means something deeper. It means energy and mass are the same thing. They are different manifestations of the same underlying quantity. Mass is just concentrated energy. Energy is just diffuse mass. They are equivalent. They are interchangeable. And this brings us back to fields. Because fields, electromagnetic fields, gravitational fields, quantum fields, they carry energy. And if they carry energy, they have mass. The field itself, the seemingly empty space around a magnet or a charged particle or a current-carrying wire, has energy density. It has momentum. It has mass. The vacuum is not empty. Space is not nothing. Space is seething with fields, with energy, with structure. And when we ask, where is the energy in a circuit? The answer is clear. It's in the fields threading through space. The wires, the electrons, the matter, they're just the stage. The real action is happening in the space between. Now, let's return to Feynman. Let's return to that hidden accountant. Because here's what makes energy so profoundly strange, so deeply magical. Energy is conserved, always, no matter what. You can transform it, you can move it, you can convert kinetic energy into heat, electrical energy into light, mass into pure radiation, but the total amount never changes. The universe's accountant never makes a mistake. And here's the kicker. We don't know why. We have a theorem, Noether's theorem, discovered by Emmy Noether in 1915, that tells us conservation of energy is connected to the fact that the laws of physics don't change over time. Time symmetry gives us energy conservation, but that just pushes the mystery back one level. Why is there time symmetry? Why are the laws of physics the same today as they were yesterday? We don't know. We can't know. At some point, physics runs into the brute facts of reality, the axioms that can't be derived from anything deeper, and energy conservation is one of them. Feynman loved this mystery. He loved the fact that energy is so abstract, so mathematical, and yet so powerful. He once described it like this. Imagine a child playing with wooden blocks. 28 blocks. Every evening, the mother counts them, and there are always 28. One day, she counts and finds only 27. She looks around. She finds one under the rug. 28 again. Another day, she counts and finds only 26. She looks harder. She finds the toy box is heavier than usual. She opens it. 2 blocks inside. 28 again. The blocks are like energy. We can't see energy directly. We can only count it, track it, watch it move from place to place, from form to form. And no matter how carefully we look, no matter how complex the system, the count always comes out the same. But here's what makes the block analogy break down. Blocks are real objects. You can hold them. You can touch them. Energy is not like that. Energy is a number, a mathematical quantity, a bookkeeping device. And yet it's the most fundamental quantity in all of physics, the entire structure of modern physics. Quantum mechanics, general relativity, particle physics, thermodynamics, all of it is built on the foundation of energy conservation. So let's reset your thinking. Let's rebuild your understanding from the ground up. Energy is not a substance. It is not a fluid. It is not a glowing aura around objects. Energy is a property of configurations. It is a number assigned to the state of a system, a number that depends on positions, velocities, field strengths, and 100 other variables. When we say a ball has kinetic energy, we mean the ball's motion corresponds to a certain numerical value calculated from its mass and velocity. When we say a battery stores chemical energy, we mean the arrangement of atoms and electrons in the battery corresponds to a certain numerical value calculated from quantum mechanics. And when we say energy flows through space, what we really mean is that the field configuration in one region of space is changing in a way that corresponds to a decrease in the energy number assigned to that region, while the field configuration in a neighboring region is changing in a way that corresponds to an increase in the energy number assigned to that region. The Poynting vector doesn't point to a river of glowing stuff flowing through the vacuum. It points to the direction in which the field's energy accounting is shifting. This is why the light bulb example is so devastating to our intuition. We want energy to be a thing carried by things. Electrons carrying energy through wires makes sense. It fits our narrative. It matches our everyday experience of trucks carrying cargo or rivers carrying water, but nature doesn't care about our narratives. Nature operates on principles that are often completely alien to our evolved intuitions. The electrons barely move. The fields propagate at light speed. The energy flows through space, guided by the wire but not contained within it. And when that energy reaches the filament in your light bulb, it doesn't flow into the metal. It interacts with the electromagnetic field of the atoms in the filament, causing them to oscillate, to heat up, to emit photons. The energy transforms from electromagnetic field energy into thermal energy into light energy, all of it described by the same abstract mathematics, all of it conserved. Let's take this even further. Let's think about what happens inside the sundae. Every second, the sun converts roughly 4 million tons of mass into energy. 4 million tons of matter. Protons, mostly, undergo nuclear fusion, smashing together under immense pressure and temperature, combining into helium nuclei, and in that process, a tiny fraction of the mass, about 0.7%, vanishes. It turns into energy, pure radiation, light and heat that stream out into space, warming planets, driving weather, enabling life. But here's the thing. That mass didn't disappear. It transformed. It converted into photons, into electromagnetic field energy, into the kinetic energy of the resulting helium nuclei. E equals mc squared is not a magic trick. It's an accounting identity. Mass is one form on the ledger. Radiation is another form. The accountant makes sure the books balance. And this is true everywhere. In every process. Chemical reactions, nuclear reactions, gravitational collapse, quantum tunneling, every single time, energy is conserved. The total number never changes. The forms change. The distribution changes. But the sum remains constant. Now, you might be wondering, if energy is just a number, just an abstraction, why does it matter? Why do we care so much about this bookkeeping? The answer is because energy conservation gives us power, predictive power, explanatory power. If we know the energy of a system at one moment, and we know the forces acting on it, we can predict its future behavior without solving all the messy details of every particle's motion. Imagine trying to analyze a roller coaster. You could track every single cart, every wheel, every bolt, every atom, calculating forces and accelerations and trajectories. Or you could use energy conservation. You could say at the top of the first hill, the coaster has gravitational potential energy. As it descends, that potential energy converts into kinetic energy. At the bottom, ignoring friction, all the potential energy is now kinetic. The speed of the coaster is determined entirely by energy conservation. No need to track every detail. The accountant has already done the work. This is the genius of energy as a concept. It's a shortcut, a way of seeing through the chaos to the underlying simplicity. And the fact that it works, the fact that this abstract number is always conserved, tells us something profound about the structure of reality. It tells us that the universe has symmetries, deep mathematical symmetries. Time symmetry gives us energy conservation. Space symmetry gives us momentum conservation. Rotational symmetry gives us angular momentum conservation. These aren't accidents. These aren't coincidences. These are the fingerprints of a universe built on geometric principles, on invariances, on transformations that leave the laws of physics unchanged. And this is where Feynman's sense of wonder becomes palpable. Because when you really understand what energy is, not as a thing, but as a conserved quantity arising from time symmetry, you start to see the universe differently. You start to see the elegance, the inevitability, the sheer unreasonable effectiveness of mathematics in describing reality. Feynman once said, "It is important to realize that in physics today, we have no knowledge of what energy is." And he didn't mean we're ignorant. He meant we've transcended the need for a mechanical explanation. We don't need energy to be a substance. We don't need it to be made of something. We just need it to be conserved. We just need the mathematics to work. And it does, perfectly, every single time. So let's come full circle. Let's return to that original question. What is energy? Energy is not fuel. It is not a reservoir. It is not a cloud or a fluid or a mystical life force. Energy is the currency of the universe's geometry. It is the quantity that nature conserves because the laws of physics are the same at all times. It is a number that we can calculate, track, and transform, but never create or destroy. And the truly beautiful part? We don't need to know what it is made of. We don't need a deeper explanation, because energy is already the explanation. It is the framework through which we understand change, motion, heat, light, matter, and everything else. When you flip a light switch, you're not sending a substance through wires. You're creating conditions, an electromagnetic field configuration, that allows energy, as calculated by the Poynting vector, to propagate through space at light speed, interacting with the atoms in the filament, causing them to emit photons. The electrons barely move. The fields do all the work. When a magnet attracts a piece of iron, there's no invisible hand reaching out. There's no physical connection. There's a field, an electromagnetic field, carrying energy and momentum through space, exerting forces dictated by the geometry of space-time itself. When the sun shines, it's not burning fuel in the way a fire burns wood. It's converting mass into electromagnetic radiation via nuclear fusion, with every gram of mass precisely equivalent to 90 quadrillion joules of energy, a conversion governed by the geometry of space-time as described by special relativity. Everything connects. Everything fits. And at the center of it all is this one abstract conserved quantity, energy. Feynman understood this. He understood that physics is not about building mechanical models that satisfy our intuition. Physics is about finding the mathematical patterns that nature actually follows, even if those patterns seem alien, even if they defy common sense. And so, if you've made it this far, if you've followed this journey from light bulbs to magnets to relativity to the sun, then you've experienced what Feynman wanted every student of physics to experience. The shock of realizing that the universe is stranger, more abstract, and more beautiful than you ever imagined. Energy is not a thing. It is an idea, a profound, powerful, indispensable idea that unlocks the workings of reality, and once you see it, once you truly understand it, you can never unsee it. The universe has a hidden accountant, and now you know what they're counting.